In this lecture, we want to talk about how to choose the binary values that will represent each of our states for a state table. So up until now in the course, we have really been treating all state assignments as being equal. And generally, we've just been listing our states in the order we thought about them and then giving a binary value accordingly. So the first state that we have, we've given 0. The next state that it goes to, we've given 1 and then 2 and so forth, or perhaps in order of a gray code. And in reality, the binary values that we choose to represent each of our states and how those transitions occur really will determine how complex our final logic will be in our logic design. And so before we get into exactly how to choose the binary values that can represent our states, we need to think about how many different options do we have for representing states. So if we had 3 states that we needed to represent, then we would need 2 bits, of course. And so for that, we can choose from 0, 0, 0, 1, 1, 0, or 1, 1. In this case, there's going to be 3 of those combinations used, and 1 will be unused. And so what you can do is for S0, just choose any of those 4. And then for S1, S1 has to have a unique binary, so you can choose from any of the remaining 3. And then S2, you can choose either of the remaining 2. And so it turns out if you enumerate all of the possible combinations of 2 bits that you could possibly have to represent 3 states, you would have 24 different choices. And so you might think about, well, let's look at those and see which ones of these combinations give us the simplest logic. Now, you can also simplify some things a little bit by saying, well, there may be some of these, even though they look different, can be formed simply by swapping 2 of the columns in another representation. So if you happen to look at representation 1 and representation 3 here, the S1 and S2 values are simply mirror images of one another. That is, you could take the A value and the B value in there and simply swap out this left column for the right column, and those would be the exact same. And you can see that is also true for the combination of 2 and 4 and also 5 and 6. They're simply mirror images of one another. And so even though those are distinct possibilities for how we represent our 3 states, if you can simply determine one of them as A and one of them as B, that is not going to change the complexity of the flip-flop logic that we will need to represent them in a state machine. And so if you were thinking about how that would be implemented, you might simply just relabel which one is A or which one is B, or for a symmetric flip-flop, meaning things like the JK and the SR, you could simply swap the inputs, so switch around which one is J and which one is K, or which one is S and which one is R. If you had a D flip-flop, what you might see is if you have a state representation where one state is simply the inversion of another, or one representation has an inversion of the states, then you might simply be able to add an inverter in the line. That might not add any complexity if instead of having an AND gate you now have a NAND to drive the D input, or instead of an OR gate you now have a NOR to drive the input. So you might think about states where one of them is simply the complement of the other, really not being any more complex than the original representation. And so let's evaluate 3 different state representations and just see what might come of this. So we see assignment A. We could have S1 represented by 0, 0, S2 represented by 0, 1, and S3 represented by 1, 0. We could also do the same thing here in B with 0, 0, 1, 0, and 0, 1. This is where we simply see A and B are swapped relative to what we had in representation A. And then over here in C3, what we're going to do is have the complement of A in there. And so this will be, instead of 0, 0, we'll have 1, 1. Instead of 0, 1, we'll have 1, 0. And instead of 1, 0, we'll have 0, 1. And so let's look at what happens in terms of our flip-flop logic. So we start out just as we have done before, and in this case, in this first slide, we're going to consider the representation A3. So we're going to have 0, 0, 0, 1, and 1, 0 represent S1, S2, and S3 respectively. And so we just develop our binary state table by simply doing a find and replace. So everywhere I have S1, I'm going to replace that with 0, 0. Everywhere I have S2, I'm going to replace that with 0, 1. And everywhere I have S3, I'm going to replace that with 1, 0. And that is going to allow us to have these states here. Our outputs are going to be exactly the same, so we'll just copy that on in. Then, if we were to do the same thing with B, we would get this table here, and so we have 0, 0, 1, 0, 0, 1, do the same kind of find and replace, and then your output here would be in the same order that we've had before. And you could finally do the same thing with C, doing the same find and replace logic. And so let's go through determining the logic for one of these representations, and I'll leave the derivation of the other two to you, the student. So if we had to determine JK flip-flop logic for the A implementation, so up here, this is our binary table that we had previously derived, and let's remind ourselves of the JK logic. So if you're currently at a 0 and you're staying at a 0, for J you need to put in a 0, for K that becomes a don't care. If you're currently at a 0 and the next value goes to a 1, then you need a 1 for J and you don't care what K is. If you're currently a 1 and you go to 0, you don't care what J is, but K has to be 1. And then if you're a 1 staying at a 1, you don't care what J is, but K has to be 0. And so down here, what we're going to do is derive the logic for JA and KA and JB and KB. What you'll also notice is we are not using 1, 1 as a state representation. So across all 4 of these Carnot maps, the 1, 1 row is filled in with don't cares, because that is not a possible state. We can never get to that state, so we don't care what the next state representation would be for a state that we can never possibly reach. Now for the rest of them, in the JA and KA, we're going to consider what is our current A value, meaning the left value here, and what is our next A value when x equals 0, the left value is here, or when x equals 1, the left value is there. And so in the first case here, we have a 0 staying a 0, so we need 0 and don't care. So that's where we get 0 right here, and this don't care right there. Then we have a 0 staying a 0, so we have another 0 and don't care here. And then finally, we go to the bottom row and we see 1 and 0, and so that's going to give us don't care and 1. So we have don't care and 1. And we have seen this before, so we'll do the same thing all the way through for our x equal 1 column. Then we'll do the same thing for B, looking at our rightmost bits. And at the end of the day, we get this logic here. xb prime for JA, x prime for KA, x prime A for J, this should be JB, and x for KB. We can do the similar derivation for D flip-flops, and so here we see, if we remember, for D flip-flops, whatever our next state is what we should put into D. So here we had all 0s for our next state, so we're going to put 0s in everything except, remember, we have don't cares for our 1, 1 everywhere. And then here we see that we had 1, 0, 1. So 1, 0, skip over the don't care, there's 1. And then we look at the right value, 0, 1, 1. So 0, 1, 1. And 0, 0, 0, 0, 0, 0. And so we derive our DA logic as xb prime, our DB logic as x prime B or x prime A, and our output Z as x prime A or xb. So here if we look at our output, again, 1, 1 is don't care, and we just fill in the column 0, 0, 1 for these three, and then 0, 1, 0, 0, 1, 0. And so, if you were to do this same approach to get the JK logic and the D flip-flop logic and the output logic for the other two combinations, B being the combination where you are simply swapping which one is A and which one is B, and C being where you have simply the complement, what you would ultimately determine is that these are the logic that we just determined, and in this case, when you're talking about JA, this is B prime, being the Q2 prime, and then this is JB, and this is A, right there being Q1. And if you compare that to what you get with assignment B, you'll notice that it is very similar, except here we have Q1 prime instead of Q2 prime. Here our logic for K is exactly the same. Our logic for J, we're simply swapping a Q2 instead of a Q1. And then down here you simply see that Q2 and Q1 are swapped. So in terms of the complexity, equally complex, we're just flipping around which one is A and which one is B. When you do the same logic with things complemented, what you see is that you get XQ2 instead of XQ2 prime. And similarly down here you see Q1 prime instead of Q1. And then down here you see Q1 prime instead of Q1. And over here you see Q2 prime instead of just Q2. And so very similar logic to what we have. And so if you compare the 24 possible combinations of 2-bit values, you'll find that most of them can be formed just by the same approaches that we've just seen. You can see either one column swapped with another column, or you can see one being the complement all the way down of an exact combination that you already have. And you also might take note that it's a good idea for our initial state as 0 to be 0, 0. And that can generally be set up pretty easily. That way we can just use a reset on our flip-flops and make sure that upon reset our state goes to all zeros. And so in this case we're only going to consider states where the default state as 0, the initial state, is going to be 0, 0. And then we see that we really just have 6 combinations here. And then we also notice even within these 6 combinations we have 1 and 3, for instance, that are simply mirror images of one another, just like 2 and 4 are mirror images of one another. And then over here we see that 5 and 6 are mirror images of one another. So really we end up with just 3 different unique combinations. And so here are our 3 non-equivalent state representations. If you were to have 4 states, you would also have 3 non-equivalent state representations, because the last state that you would add would just have the binary value that wasn't used by the 3 states you already had. Now, things start getting tricky if you end up needing more than 4 states. So if you end up needing 5 states, there's 140 distinct state assignments, 6, 420. But look what's happening when you get all the way down to 9. With 9, now you're going to need 4 bits, 4 different flip-flops, and it ends up you're going to have over 10 million different distinct state assignments. You get down to 16 states, 5.5 times 10 to the 10th power, an incredible number of distinct state assignments. And so as you get to more and more complicated designs, instead of just looking at, okay, what are all the possibilities for representing this state and the next state and other states, you want to think about, okay, what are some rules of thumb that I can use when I decide upon states being adjacent to one another and state values that will allow me to minimize my logic. And so we are going to be working with 3 different guidelines. These guidelines will allow us to simplify our logic, but unfortunately it's impossible for most state machines to follow those guidelines for every possible state adjacency. It generally is just not possible to do all of those things, and so these are going to be guides, not necessarily hard and fast rules, but as many of these guidelines as we can abide by, the better our output logic or final logic for our flip-flop inputs is going to be. And so let's look at our 3 guidelines here. Guideline 1 says states which have the same next state for a given input should be given adjacent assignments. Guideline 2 says states which are the next states of the same state should be given adjacent assignments. And so the reason for these to be adjacent is that you're not going to have much change when you have pretty common transitions. And so if you happen to, in guideline 2, change your input, and now that's going to change from one state to another, that will allow you to have as few bits change as possible when that transition happens. And so if you're looking at guideline 1, if you happen to go to the same next state, making the state assignment, the binary value representing the state assignment of 2 different states that both have a transition to the same state equal, will allow the fewest number of bits to change. And then finally, we're going to consider outputs. So states which have the same output for a given input should be given adjacent state assignments. So let's look at an example and see what these guidelines would have us do. Okay, and then we're going to think about how can we determine the binary values that we're going to use. And so in order to use these heuristics, we're going to actually fill in on K-maps where those states are in terms of what binary combinations are used to represent each state. We're going to, in all of these things, represent our initial state with all zeros. That's not required, but that makes things a lot simpler. And so in order of precedence, we're going to say, okay, the initial state is going to be all zeros. Then we're going to satisfy our grouping requirements from guidelines 1 and 2. And then when 3 or 4 states should be adjacent according to those, we're going to try our best to put them into a group of 4. Then we're going to consider guideline 3. So let's look at this state table here and see which states we should make adjacent. So guideline 1 says states which have the same next state for a given input should be given adjacent assignments. And so if you look at S0, it has S1 as the next state, so does S2, so does S4, and so does S6. And so by guideline 1, we would want to make those 4 states adjacent to one another. So that's what we have over here. Then, if you also look, S3 and S5 both go to S5. So if we can, we'll try to make S3 and S5 adjacent to one another. And then, what we see over here in the x equal 1 column is S0, S1, S3, and S5 all go to S2. Oops. And then we also see that S4 and S6 both go to S6. And so by guideline 1, these are the 4 possible groupings of states that we should try to make. You'll notice that some of these things, like grouping S4 and S6 together, also show up within this group. So maybe if we can't make this entire group of 4, we can certainly try for S4 and S6 to be adjacent. Just like here, S3 and S5 is part of this group of 4 as well. Based on guideline 2, the states which are the next state of the same state should be given adjacent assignments. So what that means is if you just look across your row, S1 and S2 are next states of S0 depending upon input. So 1 and 2 should be adjacent. Likewise, if you're in S1, your next states could be S3 and S2. And so here we have S1 and S2 should be adjacent, 2 and 3 should be adjacent, 1 and 4, 2 and 5, 1 and 6, 2 and 5, and 1 and 6. Here we also see that 2 and 5 show up a couple times, and so does 1 and 6. And so these adjacencies that show up more than once are going to get some higher priority when it comes to determining some possible state representations. On this slide, you now see states placed into a K-map. So these are some possible combinations that we could use. You'll notice that in both cases, our initial state as 0 is represented by 0, 0, 0, is indicated by A equals 0, B equals 0, C equals 0. And now, what this would mean is state S2 in the left side would be represented by 0, 0, 1, state S3, 1, 1, 1, S1 would be 1, 1, 0, etc. And so let's look, based upon these two possible state representations, and see which of these we were able to achieve based upon our guideline 1 and 2. So we wanted, first of all, for 0, 2, 4, and 6 to be part of a group of 4. We have that, so 0, 2, 4, and 6 are all in the same column. Over here we have 0, we have 6, 2, and 4. We ended up with 2, 4, and 6 sort of grouped together, but we didn't quite get 0, so that's close to being what we wanted. We also want 3 and 5 to be adjacent. You'll see that that is true in both of these state representations. We want 0, 1, 3, and 5 to be adjacent. That is what the right state representation allows us to do. And we want 4 and 6 to be adjacent. So this gets us 4 and 6, and so does the one over on the left. Based upon guideline 2, we want 1 and 2 to be adjacent. That didn't work out on the left, nor did that work out on the right. We want 2 and 3 to be adjacent. We don't have that in either of them. They're on a diagonal here, diagonal there. We want 1 and 4 to be adjacent. We don't have that here, and we don't have that there. And the more important ones, we wanted 2 and 5 to be adjacent. So we do have that here, and then also over here we do have that. And we wanted 1 and 6. And so you notice 1 and 6 are adjacent right here, and then right here 1 and 6 are adjacent. So we were not able to get all of our combinations adjacent, but we did have quite a few. And you might ask, well, why are we doing that? Why are we trying to get these states adjacent? Well, if you look at the transitions that will occur, and now here forward we're just going to consider the leftmost implementation. So we're going to consider these as our state assignments. Let's look at what actually happens in binary relative to the state changes. So if you're in these states represented by 0, 0, 0, which in this case is going to be S0, then if you go back to your transition, with x equals 0 you're going to S1. And so here you see we're going to S1. In this case we would go to S1, 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 and this allows these transitions to all be adjacent. Over here you would be going to S5, over here you would be going to S2, and over here you would be going to S6. And this is all based upon the binary values A, B, and C used to represent your current state and what next state you go to. You'll also notice that up here we have some don't cares, and those show up because of the 1, 0, 0. So you'll notice that 1, 0, 0 was not used. So if you go back here, 1, 0, 0 is an unused state representation. We only have 7 states, so our 8th state ends up being don't cares. So this allows for quite a few things to be adjacent. If we further expand this into the 3-bit binary and expand this into 3 different K-maps, what you'll notice here is that by putting these states adjacent, we now get a large group of 4 there, a large group of 4 there. This allows us to get a nice group of 4 there and another nice group of 4 down here at the bottom. And that will allow us, when we're trying to implement the logic, to get fairly simplified logic in terms of our DA, DB, and DC. And so a little bit of work on the front end in determining how to group these states could really simplify the logic that we have at the end of the day. So let's look at this state table and see what are the adjacency requirements based on this. So if we look at guideline 1 in the x equals 0 column, which states are we transitioning to together? Well, if you look at A, it goes to A. Nothing else seems to go to A. If you look at B, it goes to D, and so does D go to D. And so we might want to make B and D adjacent to one another. We see that C and F both go to C, and so we might want to make C and F adjacent. Then, if we look over at our x equal 1 column, we notice that B and E both go to F, and those would be all of the ones that we have based upon those values. So we want BD, CF, and BE to be adjacent. Guideline 2 says states that are the next state for a given state should be adjacent. So we want A and C, D and F, A and C again, D and B, B and F, and C and E. And so here we have our adjacencies based on that. And then guideline 3 says states that have the same output. And so you'll notice that A and C both have the same output for both x equals 0 and x equals 1. B and D both have the same outputs across the board, and E and F. So we might want to make those pairs adjacent as well. And so we could play around with where to map these things. We might assume that A is our default state and might make that a 0, 0, 0. And so here are some possible combinations that we could use to make some things adjacent. You'll notice that the combination on the right does not make A 0, 0, 0, but it does allow us to satisfy a lot of the requirements we had before. So if we go back, we wanted B and D to be adjacent. So let's look and see. In this case, B and D are adjacent in both of those. We wanted C and F to be adjacent. Over here, we have C and F are adjacent. Over here, C and F are adjacent. And so if we go back, we want B and E adjacent, and over here, B and E are adjacent in both. And you can keep looking at all the guidelines to see which states get adjacent assignment.